Okay, so now let's talk about the ideal vapor compression refrigeration cycle. Blah. Long name. So this is more or less what you have working on the back of your fridge. It has a compressor, that's the thing that makes a loud noise every once in a while. And then that goes through a condenser. That condenser is then releasing all of the heat that has been taken out of your refrigerator. It goes through an expansion valve that drops its pressure down dramatically, and then it evaporates inside of the evaporator, which is usually in your freezer. And that is going to remove heat from your freezer and therefore from the rest of your fridge. And it gets condensed back through the compressor. So the compressor makes it want to condense, the expansion valve makes it want to vaporize. And it keeps on going around. It works very, very well. As a note, you don't have a literal valve that you have to turn in your refrigerator. It's usually a capillary tube, which is a very thin tube. It works very well. Okay, one question you might have is, why do we not have a turbine? The reason for that is because it would be expensive. And we're not really trying to produce power with this, and we wouldn't be that much of a game. It's way too much added cost for your refrigerator. And you could have a really super thin, easy to machine tube, fairly easy to machine tube. So here's my TS diagram for my vapor compression cycle. Let's walk through it again. So from 1 to 2, I have a saturated vapor, and I then compress it. It takes work to compress it, and sets my work input at the compressor. From 2 to 3, that superheated now vapor is going to begin to try to condense. It's releasing heat as it does that. That's going into your kitchen usually. And it goes down here until it is a saturated liquid. It's released as much energy as it can, and that's all the heat going out. For a refrigerator, we don't really care about that. For a heat pump, we do. Then finally, once I have reached the saturated liquid point, I go ahead and go through an expansion valve. The expansion valve drops my pressure dramatically, and so I go down here. If it was perfectly isentropic, I would be right here. I am not perfectly isentropic because expansion valves always create some entropy. It is still isenthalpic. Its enthalpy stays more or less the same. And so I'm going to go down to this point. Okay, so I have now begun to expand. I've gone through the expansion valve. My pressure has dropped dramatically. I want to expand. I want to evaporate. Where do I evaporate? Inside your freezer. And so I'm absorbing heat from your food and other things, and the cycle continues. So this is our overall cycle for vapor compression refrigeration. This is what we're going to be using for a lot of our problems. So make sure you're really kind of used to this shape. I should actually put those up as I set them, but that's okay. As a note, this is what you use most of your AC systems and the heat pumps. Now, it's ideal. So realize that this is not the actual real world situation. We're going to get to that in just a little bit. But before we do that, let's talk about our energy flow balance. So heat in and heat out, we have that. Work in, work out. Well, there's no work out. We don't have that. That's not going to be there because we don't have a turbine. And so if we're trying to figure out what is our coefficient of performance, well, for a refrigerator, it's how much heat am I taking from that low temperature environment. For a heat pump, how much heat am I putting into that high temperature environment? And that's pretty easy for us to find because the heat going from the low temperature environment is simply the difference in enthalpy from here and here. What is the difference in enthalpy there? What's my work input? Well, it's the difference between these two. So I just take a few differences. If I know those points, I can solve everything. The one thing I really like about these coefficient performance equations is just that they're so simple. Just think to yourself, how much energy am I trying to move? Where am I trying to move it from? And how much work did it take to do that? And then it's pretty easy to find your equations and figure out what you're missing. So don't forget that. It can be very, very helpful. Other little details to make it easier for us. Point 1, we typically say, is a saturated vapor at whatever pressure it's set at. Makes it easy. And point 3 is a saturated liquid. Point 2, superheated, not so easy there. But we have 2 points where we know their quality and it makes it very simple to calculate them. Okay. Now, one thing they did do, even though they say this is ideal, is they did say that the throttling process was generating entropy. They could have just put this line straight down and made it even simpler. But it's not all that much of a change to make a slightly diagonal line. So this made it a little bit closer to an actual system. So what would an actual system actually look like? It would look like this. You're like, that's exactly the same thing. Yes, it is. But now let's start accounting for all the issues we're going to run into. Okay, let's count for all the issues that we're going to run into. So what are the differences? First off, compression, it's not isentropic. Now, it's not a really good deal breaker here. You can use the ideal case and then correct it, which is what we're going to do. But compressors, they're usually very efficient, but not 100%, like 95, 97, you can see that. Okay, second thing, at the evaporator exit right here, even though I was supposed to have gone down to a saturated vapor, I'm actually superheated vapor at that point still. So that's not going to make me less efficient. At the condenser exit, I am actually not a compressed liquid perfectly, I'm a subcooled liquid. And also, as I go through the condenser and evaporator, I am losing pressure. You go through a tube for long enough, you're going to have a pressure drop. So all of those things make my ideal cycle look much more like this actual cycle here, the actual cycle. And that's the 2' that you can see right there. And all the rest of them are kind of the same points. So we have some issues. There's a lot of differences there. And because of this, it's going to reduce my coefficient of performance. So, like we always say, ideal cases, we calculate them because they're great upper limits. And if we really want to compare it to the best thing, we compare it to Carnot. But when we're trying to compare it to a more realistic case, we use ideal cases. So next time we're going to go through a problem and actually show you how you can calculate some of these coefficient performance and just performance of a refrigeration cycle for an ideal case. Thanks for watching. I'll see you all next time. Bye-bye.